Welcome back, everyone, and in this video we're going to continue doing more Quaternion constraints and limitations. So in the first video we did a cone constraint. The last video we did a hinge constraint. Now today we're going to do a ball constraint. A ball constraint is function similar to a hinge constraint, except this way, but in a sense that we're still dealing with planes. This kind of creates like a 2-degree, 3-degree freedom of movement. I'm not exactly sure if it counts as 3. Maybe it does. But it's basically like a ball joint. You know, you have a ball joint, and it can go as far as it's allowed to. You know, essentially, you know, it's just how far can the sphere rotate? You know, what's the limit? So we'll get straight to it a little bit. So just like in the other previous videos, we have to determine an axis. So I'm not really going to go step through this again. Just watch the previous 2 videos about it. So we determine an axis that's on a circle as the forward direction. Once we have the forward direction, we can then determine its up direction and its left direction. This just allows us to help define everything, because we need to define the limitation. So the way the ball constraint works is that, let's just say we have a ball, right? And sometimes you'll see like a ball socket, and the ball socket is like this. So you kind of have like a little, I don't know what you want to call it, like a holder for the ball socket. So this ball socket can only rotate till it reaches this limit. So let's say if there's like a little screw or a hinge or a pin or something sticking out of this ball, it goes as far as this ball joint allows. If you had like a smaller ball joint where it ended up here, then this can rotate even further. Get my drift? It's a ball joint. Images.google. Probably should have done this. Ball joint. Yeah, pretty much similar to this. These things are kind of like ball joints. That's a ball joint. If you play with cameras, you should know this ball joint. You know, going through this little hole allows it to be about a 90-degree rotation. But here, when going in this axis, it's actually limited by its range. We're not going to create something like that where it has 2 different. We're going to just do a basic ball joint. More in terms like one of these. So that's kind of the ball joint that we're going to create. But we can define how far its circular rotation can be. So how do we do that? How do we determine that, right? So here's our ball, and we're going to deal with this all in basically 3D. So I'm going to pick a direction. So our 4 directions over here. So I want to define, let's say, maybe 45 degrees of rotation, or 5 degrees of freedom. So I'm going to, since it's going to be a sphere, it's going to be 3 dimensions. But in 2D, I basically want to define that this is my degree of freedom. 45 and another 45 in all directions. It's kind of like the hinge joint. It follows a lot of similar processes. Now, the only difference is that where in the hinge joint, this was the plane. This is not the plane that we're gonna do the constraint with. What we're going to do is take this point on a circle that's on this rotation plane. Yes, we're going to do that. And then we're going to project it onto the main point. This creates a point on the z-axis. So we know how far in the z-axis can we go. So if this here is basically 180 degrees from here to here, or whatever, from this side to here. Maybe not. Yeah, whatever. So yeah, whatever. So that's 45 degrees from this point going in this direction and in that direction. So what we would do, since we know what that center point is, that center point on the z-axis, this point on the z-axis can act as our point of will act as our point of our plane. And we already know that's our forward direction. We know that this is our up direction. And we know this point pointing at the screen is our left direction. So we're still going to use the same axis, the axes, wherever, that we defined by finding the forward direction. So by using that point, we just get to grab a radius and we're going to create a cut. So basically, we're going to cut this piece off out of the circle, and that becomes a hole. So essentially, that's what we're going to do. We're by creating a 45-degree hole in our sphere. So that chunk that we remove, I don't know if can I use. Can I? No, I can't. Whatever. So I'll just do this. So this part is no longer viable. Like, this is the part where everything can kind of just move freely. Once it's outside of that range, that radius, outside of this radius, then we have to snap it back. And we snap it back kind of like how we kind of did it with the cone constraint. So it's kind of a mix between some of the things we did with the cone and some of the things we did with the hinge. So that's it. And like I said, you can pick any degrees you want. Like, let's say if you want like 107 degrees. So you go here, you'll go here. So that's our point. And then we end up doing a cut. And that means everything outside of here has been cut off. And the only limit is here. But you got to think about it. Our center ball is here. So that means I can rotate all the way to here. And I can rotate all the way to here. This is where I stop. And this globbly mess is the logic between our ball joint constraint. And, to do the snapback, we do the projection and things, blah, blah, blah. So we'll go into the code. And, of course, I visualize everything. And so this way it's a lot easier and better drawn than what I do by hand. All right. So, like I said, we define an axis. And our gray line is how much degrees we want. I think there's like a 20-degree range. So from the forward direction, between the forward and the up direction, I define 20 degrees. All right, I don't want that. So like right here. So we set the limit to 20 degrees. Like I said, a lot of the code's the same. Not much has changed. The only thing that we're going to define our ball constraint, like I said, it's our rad limit, like it's our angle limit, our plane radius, and our plane position. Those are all that we need. So in our limit function, we could just convert everything to rads, and this shows our gray line. I forget what does this do. So after that, so what we got to do next is we got to take this point and project it onto this line. So we can kind of figure out where does this show up. Let me just do this. All right. So, we've done projections enough already. So, I don't know. We've been doing so much. So we get the dot product of V, which is the gray line and the green line creates a dot product, creates a length, and that length I can then apply to the green line to determine the closest point. And this can be visualized right here. Boom. And now with that point, the black dot point discovered, like I said, it's the closest point from that to this line. What do we do? So that's what this is when we scale it. And now to get the radius, we subtract our gray point from our plane position. So this point, from this point, we then just get we do subtraction from those 2 points, and then we get the length. And that creates a radius. So let's just quickly recap. So the point that we're we're setting up the limits. So we're setting up the limits. So this is the limit of degrees of how we want to go. We project it onto our forward direction. We get the closest point. We subtract those 2 points. That creates a radius, and that then creates our plane, basically, because that point becomes the center point of our plane, and everything's still the same. It's still Z goes in that direction, up still goes in that direction. Just think about it going in that specific. So if anything, this is still the up direction. The blue and this black line is still the same direction. So we can sit here and I can show you the debug sphere and debug plane. And if we click refresh, there we go. So there's basically our sphere. So you can kind of get an idea what our sphere looks like. It's a unit sphere. And like I said, we did a projection. Now we created that circular plane. So we kind of cut a hole in our sphere. And that's the hole I googly glopped I drew. So that's our limit. That's our visually, this is how far our limit is allowed to go. So let's comment out some of these visuals because we don't need all these visuals here because they kind of get in the way. Refresh. Okay, so because that's all we care about. We just care about our sphere and we care about the hole in our sphere. And you can, like I said, you can change it. It can be anything you want. We can do 170. And there you go. From this point to here is this point over here where the circle is 170 degrees from here as the origin point. So the hole is in the back of the circle. So like I said before, everything on this side is gone. This is really that little sliver is what's left of the circle. We actually cut up most of the sphere away, but we're not doing it that way. We're gonna cut the small hole because it's easier to see and visualize and think. So there we go. That's our hole for now. All right. So now we're going to apply the direction that we want to test. So as you can see, this gray line represents the rotation that we're testing. That's where once we multiply it by the forward vector, it gives us that position. Okay, so the first thing we're going to do is we're going to get the length between these 2 points, which then allows us to create a specific angle. Get rid of this. Don't need this right now. Now, it's probably harder for you to visualize it, but this is the length vector between this green dot and this gray dot. So between it's not the green dot. It's really it's like really right here, the plane position. Do I want to debug plane? Why not? So maybe I'll make it easier if I visualize the plane position. Excuse me. Refresh. There you go. So this way, if I tell you where I'm actually, so all right, so much better. That red dot and that gray dot, that's what this black line represents. It's the length vector between the two. So the idea is, if we're going to treat this, let's say if we're going to treat this black line as if it's here, we can ideally shift everything to origin. So what we're really testing is between the green line and the red line, because even though this plane in the center is there, it still shares the same forward direction as the sphere. So we can actually shift everything. So we can just use that. It's, like I said, it's still the same forward vector, and it's still this vector here. So when we do a dot product between the green line and this dot, this one, it will tell us that it is. So if we, like, let's say we use this line right here, where the green will be 1, blue would be considered 0, over here would be considered 0, and if we had a dot over here, it would be considered -1. As you can see, by using that dot product between green and black, should be normalized. I think I do normalize it. It creates a value that's in the negative. So it's below this axis, which essentially is really behind this point. Like I said, everything got shifted into origin for testing, because so we can use dot product easier. But what we're really testing is this point in front of this plane or behind this plane. That's what we're testing for. We're doing a very easy test. If it's behind this plane, then it's outside the limit. It shouldn't be there. Like, remember, everything has to be inside the hole, not outside the hole, because that's where the hole is. That's where everything is free. So since it's behind the plane, then we have to apply constraints. If it was over here, the dot product would be in the positive zone. Because you got to think about it. Like I said, these two ends on this plane we're using a dot product, using the forward vector, will create a value of 0. Everything on this side is positive, everything on this side is negative. So by testing it, if it's negative, we have a problem. So we got to snap everything back. So that's what's going on. So yeah, that's everything that's going on right here. So we have a point. We figure out that direction, and then we create that dot product between that direction and the z-axis. Like I said, if it's less than 0, we have a problem. All right. So now we need to. So now what's the next step? So we know we're behind the axis. We need to actually start projecting this onto the axis. So another thing we're going to do is just like how we define the plane by projecting to find the closest point on it. We're going to do the exact same thing. We're going to project the gray dot and the green dot together to find the closest point on this line, which would then define how far away this point is to the closest point on the plane itself. So if I comment this out. So, and you can use the dot product to scale the z-axis to actually find the point. So if I refresh, let me just double check the z-len. I had to do a bunch of things to get the visuals to display correctly, but this creates the length. This v length is what creates essentially the length to solve for this orange dot right here. So what the length that we get from here to the green dot is here. So from here to here, is it? No, it has to be from here to here. wonder if I did this wrong. I think I might have to use this, really. Well, I don't know. It works. The source code works, but I tested a lot. I don't know. Like, to me, it feels like I actually get something slightly wrong, but no, it works. Yeah, what's the dot product? The z-axis and the length. Yeah. Yeah, that's why I have to use the z-axis with the dot product, because I used z-length. So either way, by using the dot product, we can get the closest point, which is about the same is the length that I need to get to the plane. And then v position is I take direction, which is the gray dot, subtract by the length that we're moving. So the length from here to here, basically I add it to here and it gets that point. And at that point, so now we have this projected onto the plane. But now we need to get it to the closest point in the radius. So what we're going to do next is we're going to get the range between the red dot and this orange dot. And then normalize it and then just put the radius. So I should visually show it this way. So here it is originally, and then this is when the radius and yeah, that's from here to here. That's the maximum. Should be the maximum. And yeah, so like I say, you project it, you get the distance between here and here, and then you normalize it so it becomes a normal direction. Then you multiply it by the radius, and then you apply that new value to the red dot. It becomes like an offset, which then creates this point. And that point, like I said, is the snap position, and then we use that as the point to do the look rotation. So yeah, like so that V pose, we subtract from the plane pose, we normalize it, we scale it, then we add it back, and we're all done. And we use it to the look rotation. And that's it. And that's how we got the ball joint. And if I wanted to, I could change my limit to a much higher value. Let's say try 80. 80 degrees of limitations. And again, there's the pink dot that tells me that it was over the limit. And here you go. Now this is about 80 degrees from green, and the gray dot is on this side of the plane, so I don't need to do anything else. If it's on this side of the plane, it's on the positive side, we're good to go by using the dot product between here and here. And that is 23 minutes to explain how to constrain a ball joint. And yeah, just like the other constraints, you can change the axis, and everything kind of just works. So I changed the axis, now that's forward, and there's the axis of everything has to be shifted up. So that one gets rotated a little bit up, so it's at least parallel to the plane. And yeah, that should give you the rotation. I know so many lines and dots, it starts to get confusing. But yeah, that's forward direction, that's up. And can I change this? Maybe 15, 17? Maybe that. Whoop. I probably made it lower. Let's see. I think I had this set already. So refresh. Yeah, I don't know. I totally forgot some of the samples, but like I said, all these are just like samples to show you. You know, this is a better example. Like definitely, yeah, it's right on the plane. So everything just works out. You know, I kind of like the fact that it's just basically just based on the plane. So once you define the plane, you have to check to see if you're on the right side of it. You know, if you're on the positive side, you're golden. If you're on the wrong side of it, then you're not golden. And you just gotta, you just gotta just snap it into place. Which is, you know, like I said, it's a couple more projections, and then, you know, getting it projected on that plane, and then once you're on that plane, then grab just snap it to the radius of the circle, and that's all you got to do. So, like I said, you keep that angle. You know, it's an angle. And the one really nice thing you probably should do in your animation is, like, if you know you have to snap, instead of just snapping automatically, maybe apply like a tween to it. So you ease into the snap. So it's not so clunky, unless you want it to just instantly go to it or whatever. But yeah, it's so messy, but it works. It works. You know what? Those samples probably work based on the original orientation. That's probably why. Ooh, so messy. But yeah, no matter what, everything still gets snapped into place. Is it over the top? Okay, it's going over the top. This problem goes from below, which is probably the example we had to begin with. Refresh. It goes from below. And access off. I don't think you need to have an access off. Refresh. Access off must be from the hinge joint. Either way, like I said, it still constrains no matter what you throw at it. So yeah, I don't want to waste any more time. So there you go. Hope you enjoyed it. This was the ball joint constraint. And like I said, you can change the limit to as far as you want. You can make up to like really 179 degrees. You really don't want to go over that. The limit should be 179. I did put a limit for 80. 80 there's no limit at all. It means you have a 360 degree rotation. So in all honesty, that is a small little bug in the limit. Like it, the hell. So it really should be 179. That's the only thing you can't do. Like I said, it's no longer a limitation if you can go a whole 180 degrees rotation in all directions. So yeah, that's probably the only fix you really need to do to make sense. You know, you don't want to get that bug in there. So yeah, that's about it. Let me clean this up a little bit, and then I'm going to update GitHub with this little fix. And yeah, that's it. That's our ball joint. Hope you had fun. This is probably the last constraint I'm going to do for a while. I don't know of any other constraints that are important. You got the ball constraint, you got your cone constraint, and you got your hinge constraint. Yeah, that's about it, really. Ball constraint. The only thing I could probably do is another cone constraint, but you can change the X and the Y. So instead of being a circle, it's more like a cone, but with an oval bottom. That's the only other constraint you could probably do. That might be a little bit tricky to do. But yeah, I can't think of any other constraints we can do for rotation, because I haven't really used constraints in Unity, so I never got into it. I just know these 2 or 3. By searching around that, what's the important constraints when you're dealing with body, dealing with the human body. Like if you do anything mechanical, a hinge constraint is very good. And then certain parts of the body would be a cone constraint or a ball constraint. Would work, for your hip, your shoulders, things like that would do a good job of creating those constraints. Like pretty much your shoulders and your hips or your legs, they're going to be on a ball constraints. Most likely, you just got to just make sure you got the right access, the right degrees of freedom, and you're pretty much golden. And like I said, hinge is mostly for mechanical. I don't think there's anything on the human body. Oh, the elbow. That's right. The elbow and the knees are a hinge constraint. So ball joints, shoulders for like the hip, thighs, whatever that ball is called, and elbows and knees are hinge joints. And mechanical things like a door, a box that's opening if you really care. But if you have a box animation, you're not going to add a constraint to it. But yeah, that's it. That would be, like I said, last constraint. If there's another constraint that you guys are really interested in, tell me, give me some information about it, and maybe I can figure out how to create something like this to illustrate and create a function that allows you to limit the movement of a Quaternion. So, like I said, all these constraints follow like the same thing. You define an access, and most often you always have to define a plane to help. Even the cone constraint, you create a plane. You create a plane similar to how we did with the ball, but instead of going inward, it goes outward from the center. So, all right. So yeah, I probably said this already. So again, please like and subscribe, and see you guys in the next video. Bye.